Today, we're going to be talking about cloud-native Apache Spark, why and how to migrate your Spark pipeline to Kubernetes. Thanks, Dot, for having us, by the way, at Skill by the Bay. You, you already gave the personal introduction. I used to be a software engineer at Databricks. Now, for the past 2 years, I've been working on data mechanics. And when I'm not working, I like to do some trail running, like with the photo on the right. So before I jump into the topic, really like deploying Spark on Kubernetes, why to do it, how to do it, I just want to give a few words about data mechanics so you have a bit of background, how come I'm knowledgeable about Spark on Kubernetes. So our goal at Data Mechanics is to make Spark easy to use and cost effective with a focus on data engineering workloads. Easy to use, through the Dockerization. We'll be talking about this later, but obviously that's one of the benefits of running on Kubernetes. We also have some intuitive user interfaces so that you can track your logs, track their metrics, and we have some integrations with the tools you already use, like Jupyter or Airflow. How we make Spark cost effective. It's a long topic, but one of the main things we bring to the table is automated tuning. It means that our platform is going to automatically tune infrastructure parameters and Spark configurations, like the amount of memory and CPU to allocate to your Spark executors, like the type of disks, like some Spark configs around parallelism, around shuffle. And we're going to be managing the node pools of Kubernetes. We're going to automatically scale them up and down based on load. We're going to use a mix of spot and on-demand instances if you want to again reduce your cloud costs. And this slide is maybe the most important because it's most relevant, obviously, for our talk. Our platform is deployed on a Kubernetes cluster inside our customer's cloud account. So in fact, if the customer uses, say, Amazon, we would be deployed on an EKS cluster. And in fact, we create and manage the Kubernetes cluster for them. On this cluster, there is one instance running all the time that we call the gateway. And the gateway is the entry point for launching Spark applications, whether these are interactive notebooks or whether these are script or Airflow applications or coming from any other scheduler. Once the request hits the gateway, we're going to actually launch the Spark pods, configure them, scale them, and give you access to a monitoring UI. So as you can see, our entire product, our entire startup is built on top of Spark on Kubernetes. And so this is why I want to talk a bit about it today. So first, we'll go over the core concepts of Spark on Kubernetes. Then we'll be talking about really the reasons why more and more companies choose Kubernetes. And then we'll go through like concrete tips to help you get started with Spark on Kubernetes. So a setup checklist, some best practices around performance, around cost efficiency, around monitoring. And at the end, we'll be talking about the future works that are happening for Spark on Kubernetes in Spark 3.1 and beyond. Great. So first, before I actually even talk about Kubernetes, just a recap about Spark. I mean, it's a distributed analytics engine for big data and machine learning. The reason why Spark is popular: first, it's fast. Second, it's easy to write a Spark application because you can, there are these high-level APIs in Python, in Scala, in SQL, and more. And last, it's versatile because with Spark, you can do obviously ETL and data engineering. That's the most common use case, but also interactive data exploration, machine learning, streaming, and so on. Now, where does Kubernetes fit within Spark? Well, one thing that Spark doesn't do is manage the cluster, manage the containers, manage the executors. It can request executors, but it's not going to launch the instances to run them. So for that, it needs a cluster manager. And Kubernetes is a new cluster manager for Spark. The other cluster managers are just Standalone, which is built in with Spark, Apache Mesos, Hadoop YARN, which is by far the most common cluster manager today, and Kubernetes, which is the new kid in the block. It's been available since Spark version 2.3 in 2018. So what do we mean? What happens really when you submit a Spark application on Kubernetes? Well, we say that Spark runs natively on Kubernetes because there's a direct communication between the Spark driver and the Kubernetes master. So when you submit an application, it's first understood by the Kubernetes API server, who is going to then start the Spark driver pod. So basically the Spark driver container. And then the driver container and the Kubernetes master are going to be directly talking to each other to request more executor pods. And once they're ready, obviously start running tasks on these executors. And in fact, this communication can happen during the lifetime of the Spark application if you choose to enable dynamic allocation. Now, there are two ways to submit Spark application on Kubernetes. The vanilla way is Spark submit. So this comes from Spark open source main repo. App management is a bit more manual, but it works. There's an open source project that was developed by Google that is called the Spark-on-Kubernetes operator, and it is a bit more popular because it provides a lot of sugar and nice features on top. Typically, it gives you tooling to read logs, configure your app, kill it, restart it, schedule it, as if it were a Kubernetes object. So to show this in practice, if you use Spark Submit, well, basically you're going to provide the URL of the Kubernetes master, and that's the only difference between doing a Spark Submit over, say, Yarn and Kubernetes. But then if you want to interact with the application, well, you're just going to have to interact with Kubernetes pods directly. Now, if you install the Spark on Kubernetes operator, well, you start defining a Spark application and you can manage it as a Kubernetes object. So you can read the logs, describe the application, even schedule it, and so on. So honestly, Spark on Kubernetes operator would be my recommendation. The only downside is you need to install one long-running system pod to have this operator running, but it's a very small overhead overall. Okay, so now that we have the core concepts of Spark on Kubernetes, let's look at the main reasons why companies choose to run Spark on Kubernetes over Yarn. So first, that's probably not a surprise, but one of the main benefits is just containerization. So with Kubernetes, you're going to be able to package your applications with Docker, and well, that's going to give you a very tight control of your environment. It also means that you're going to be able to use the same Docker image and run it locally, maybe for development, for testing on a subset of the data, and then run it at scale on the Kubernetes cluster. The other benefit is obviously you're going to be able to package all your dependencies this way. You can also change the major Spark version. And obviously you're going to have the exact same environment, whether you're in dev, test, and prod. And last but not least, the iteration cycle while developing with Docker can be really fast. It's not true to say, oh, it's going to take forever to build and so on, because Docker is going to cache the previous layers of, if you're iterating on your app, you probably push the Docker image at least once. And so overall, you can get of an iteration cycle of maybe 20 seconds between the time you make a change on your laptop to it runs at scale on an application on the Kubernetes cluster. Well, the second benefit is it's just the benefits of a shared infrastructure. On Yarn, you have little isolation. You typically have a global Spark version, a global Scala version, some global dependencies. And so as a result, there can be I guess, impacts from running multiple Spark workloads on the same Yarn cluster. And if you want, your application to be really isolated and stable, you're gonna spin up a YARN cluster for just your single Spark application. So what we call transient clusters or single tenant. Now on Kubernetes, you have a full isolation and control that just comes from Docker images. And so what this means is, even though you're going to have multiple Spark applications on the same Kubernetes cluster. And so what this means is you get kind of the best of both worlds: isolated applications and the cost efficiency of a shared infrastructure. What's more, Kubernetes has a lower overhead than YARN when it comes to, starting nodes and starting containers on it. And so you have a really fast startup time. Basically, if a node is already available, it takes maybe 5 to 20 seconds to start a Spark pod. And if a node is not available, then you need to get it from the cloud provider, but that's pretty fast as well, maybe 1 to 2 minutes. The last benefit from using Kubernetes is the ecosystem of the Kubernetes or Docker compatible tools. So first, Kubernetes is the cloud provider abstraction. So it means if you build Spark on Kubernetes, there will be very little lock-in compared to building for a specific platform or specific cloud provider APIs. And then you get lots of open source projects for free around the CI/CD, logging and monitoring, networking, security, and so on. So I would say, yeah, these are all the main reasons why companies more and more choose to run Spark on Kubernetes over YARN. Now that we went over the motivations, let's talk a bit about how to actually, get started, how to migrate your Spark apps from YARN to Kubernetes. So we have a bit of a checklist here. I won't have the time to go into every end-to-end way to get started, but the basic setup is obviously you need to create the cluster with proper networking, data access, and node pools. I would then recommend to install the Spark operator, which I mentioned earlier, and also the cluster autoscaler, which is an open source project which will dynamically add nodes to your node pools when the Kubernetes cluster would benefit from it. On the monitoring side, I'll go over this later, but you probably want to have some collection of logs and persist them to storage, and similarly for system metrics and for Spark UI. And in terms of some important optimization stuff, you should use local SSDs to improve the performance of shuffle. That's pretty critical. And also maybe configure spot nodes and optimize your applications so that typically you're not wasting too much room on your nodes and your pod bin pack efficiently on the Kubernetes nodes. So let's dive into a few of these topics now. So first, performance best practices. This is the number one gotcha when people start working with Kubernetes. Let's say you have nodes that have 4 CPUs. And so pretty naturally, you're just going to submit an application and say spark.executors.cores equal 4. But if you do this, you realize that your executors will be stuck in a pending state. Why? Okay, because even though your nodes have 4 CPUs, there is a small number of resources that will be reserved for Kubernetes and system daemons. So the node allocatable isn't quite 4 CPUs, it may be just 95% of that. Then if you're running daemon sets, this could be another small overhead that goes to your daemon sets. Let's say that at the end, you have 3.6 CPUs available for your Spark pods. Well, then, when you configure Spark, you should set this config spark.kubernetes.executor.request.cores equals 3.6. And then Spark executor cores can still be 4. And when you do that, you realize that you're actually over provisioning a little bit the number of Spark executor cores compared to the actual CPU request. And in fact, the two numbers could be decorrelated. So you could say, oh, Spark actually, you could tell Spark, oh, actually I have 8 cores, but still have only 3.6 CPU allocated. And that's really called over provisioning. In some cases, this can be beneficial for performance. If basically your CPU isn't usage isn't that high, it's something that could provide a performance boost. All right, this is the kind of settings that is automated, by the way, on our platform. So now a critical, performance tip around shuffle. So we published a blog post with a benchmark where you could find the results and learn more. But just the TLDR is that you should use local SSDs whenever possible. You should look at your cloud provider to know how that's done. And it's not enough to just use them. You should also configure Spark to be able to actually use them. And so here on the right, we're showing you how to do this with the host path, that gives basically the path to the mounted disk. And there can be performance gains of up to 10x on IO-bound workloads. So it's really worth it. It's worth the additional price of paying local SSDs. Now, if for some reason local SSDs are not available, then the other important parameter is the size of your disks, as disk latency and throughput is almost proportional to disk size. So here this is the plot of the ratio of the query duration that we got while running the TPCDS benchmark, once with small disks and once with larger disks. And you can see that for shuffle heavy queries on the right, there was a ratio of 5. So you basically, your query would run 5 times faster if you just increase your disks. I forgot by how much we increased them, but this will be shown in the blog post. So that's the second tip really on shuffle performance. Now that we covered, shuffle performance, let's go over cost optimizations. So one thing that we do at Data Mechanics is we configure the Kubernetes cluster to have multiple node pools, and these node pools should be able to automatically scale up and down, and also scale down to 0. Okay, not so that you're not paying anything when you're not running any workloads. So typically we might have a small on-demand node for some system pods like the Spark operator we mentioned. We might have an M5X large node or node pool for driver pods. And so here it's important to have them on demand, because you don't want to lose the driver if there's a spot kill, because that would kill your application. But then Spark executors, these are fine to put on spot nodes, because as you know, if you lose a Spark executor, the application will still continue. It will lose some work, you'll have to redo some work, but it will continue. So here's an example setup on Amazon EKS, where we had to define a labeling scheme for our nodes. So we have basically 2 node labels, let's say lifecycle and instance. The lifecycle is to decide between spot and on demand, and the instance is to use the instance type. And then you're going to have to manually create auto-scaling groups and assign them corresponding tags, and then use those labels as tags to basically inform the cluster autoscaler. And this way, when you submit a Spark application based on certain node labels, the cluster autoscaler will place them on the node pool of the right tags, and maybe scale the node pool if necessary. So let's look at here maybe the example with the Spark operator. You could say, oh, I want my driver to be on a preemptible machine. Well, I think this should say on demand, and I want my executor to be on spot. And so basically that's how you would achieve this. Great. Yeah, another thing about cost reduction is dynamic allocation. So dynamic allocation is a way for the Spark driver to add or remove Spark executors on the go. Dynamic allocation is available on Kubernetes since Spark 3.0, so it's available through a mechanism called shuffle tracking. What's shuffle tracking? Basically, the Spark driver will track which Spark executor is holding an active shuffle file, and these executors will not be scaled down. So this is the configuration that you need to enable to make this happen, and it works. It works pretty well. We'll see that in Spark 3.1 there'll be another improvement to dynamic allocation. Yeah, maybe one last trick around well, how to speed up dynamic allocation or how to speed up application startup time in general. And this is something that we also enable in data mechanics or make it configurable. You could choose to over provision the Kubernetes cluster with some low priority pause pods. So a pause pod is basically a pod that does nothing. And if, let's say, an application requests a new executor because of dynamic allocation, well then, since the pause pod has a low priority, it will get evicted by Kubernetes. And so the Spark executor pod will take its place. And then the pause pod will be rescheduled again, and this might trigger a scale up. And so you see that pause pods is basically just a mechanism for you to over provision the Kubernetes cluster a little bit, pay a little bit of additional cost, but then have a lower latency for your applications. It's definitely a better option to do a bit of over provisioning than to have a fixed size Kubernetes cluster where you would be wasting much more compute on average. Right. So now monitoring, yeah, this is important. So there are a few different monitoring options available to you when you run on Kubernetes. One of them is the Kubernetes dashboard. I've put a link. I'll send the slides afterwards, by the way. But I've put a link with the instructions to install it on EKS. And so, well, it gives you a general purpose monitoring dashboard where you can track metrics for all your pods. The only issue is that it's not specific to Spark, so it's hard to really reconcile what's happening with your actual jobs and stages and tasks. And the other issue is that executors' metadata is lost when the Spark app is completed. The other option you have, as you see, is the Spark UI. So for live applications, it's pretty easy to access. You just need to port forward the Spark driver on a certain port, 4040, and then the Spark UI can just be accessed on your laptop. And then if you want to have access to Spark UI after an application is completed, you need to set up what we call the Spark history server. To do it yourself, you should write Spark event logs to a persistent storage. You can use a config for that, and then you can install the Spark history server using a Helm chart and follow some instructions to give it the permission to read from the persistent storage. Now, as of today, actually, we have just released a new way to have access to the Spark history server. This is, we have an open source Spark agent called Delight, which will stream metrics to our backend at Data Mechanics, and then you could view the Spark UI for your application at this URL. And this is a free and cross-platform product. Right now, it's just a free hosted Spark history server, but as of January 2021, we hope to release what you see here on the right, which is basically a Spark UI replacement with new metrics and a better UX. And so this free Spark history server is just the first milestone. And then in January, hopefully we should have something much more exciting to you. Great. Last but not least, I see I have another 3 or 4 minutes. I just want to say a few words about the future works for Spark on Kubernetes. In fact, I'll start with just a timeline to remind you that yeah, the first support of Kubernetes came out with Spark 2.3 in 2018. Then in November, Spark 2.4 came out with some critical features like support for client mode, volume mounts, dependency management improvements. Then in June of this year, Spark 3.0 came out with the dynamic allocation that I already mentioned. And next month, or maybe in January, we'll see Spark 3.1 should be released. And this is an exciting day for Spark on Kubernetes because the experimental label will be removed, okay? So Spark on Kubernetes will be declared GA. Because today, if you look at the official documentation of Spark, it says that it's currently experimental, but we're going to actually call it a GA. And another feature that I'm really excited about is a better handling for node shutdown. So what does that mean? This will happen in a few different circumstances, typically during dynamic allocation on downscale, or if a node goes down, for example, because of a spot kill. So what will happen? Kubernetes will warn the node of the imminent shutdown. Then the Spark driver will stop scheduling tasks on the executors, okay, because we know it's going to go away. And very importantly, we're going to copy the shuffle and cache data from this executor who's going away to an executor who's going to stay. And what this means is that the Spark application can basically continue unimpacted. So this will make Spark a lot more resilient to spot kills, and also it will also make dynamic allocation a little better. Another feature that I'm looking forward to, but more for later in the future, is to use a remote storage to persist shuffle data. I'll quickly go over that. So what this means is that shuffle file will first be written locally, then it will be asynchronously copied to S3, and then on the reduce side, when you need to fetch a shuffle file, if for some reason the original executor is gone and the fetch fails, well, then we can just fetch the file from S3 instead. So again, this will make Spark much more resilient to node loss. It will completely disaggregate compute from storage, which is something that we always try to achieve. And so I'm also really looking forward to that. Great, I see that I'm at the end of my half hour. I hope this was useful, and I will now join the other chat for a live Q&A. Thank you all very much. Feel free to connect with us on our website, on LinkedIn, or Twitter.